Hi everyone. In this lecture, we are going to talk about greatest common divisor. Okay. First of all, we will discuss what is GCD and what are the various approaches or the algorithms that we have to compute GCD. Okay. So GCD, as it says, it is the greatest common divisor of two numbers. Let's say the numbers are, let's say 8 and 20. Okay. Then we need to find a number x which divides both 8 and 20. Okay, so a brute force way of computing the GCD would be, um, we know this number would lie in the range starting from 1 till minimum of the numbers that we have, 8 and 20. Okay, because you cannot have a number greater than 8 which will divide both 8 and 20. Okay, so the number would be at max the minimum of these two numbers. Okay, for example, the numbers are, let's say, 5 and 20. Then I can say GCD will not be greater than 5. Okay, and in this case 5 is the GCD. So let's talk about 1. Does 1 divide both? The answer is yes. So 1 can be a possible answer, but we need a greatest number. So let's go talk about 2. 2 divides both 8 and 20. So 2 can be an answer. Let's increment our number. Let's talk about 3. Does 3 divide both 8 and 20? The answer is no. Let's talk about 4. 4 does divide 8 and 20. So 4 can be an answer. What about 5? 5 does not divide. 6 does not divide. 7 does not divide. And 8 also does not divide. So we iterated from 1 to 8. Okay, that is the minimum of these two numbers. And we find out 4 is the largest number that actually divides both 8 and 20. So GCD of 8 and 20 is what? It is 4. Okay, so this is a brute force algorithm, and the complexity of this algorithm would be, let's say this number is a, this number is b, it would be order of minimum of a comma b. Okay, that's the complexity of finding GCD. Now let's talk about another algorithm that is that we generally do on pen and paper. Okay, and we'll try to code it. It is also known as Euclid's algorithm. Okay, Euclid's GCD algorithm. So first we will learn about the algorithm in this video, and then we will discuss the complexity in the next video. So what it does, we say, okay, let's keep 8 and let's keep 20 here. Let's say the larger number is a, the smaller number is b. So you keep a inside, okay, and you keep b outside. So let's say a is 20 and let's say b is 8. So what we do is we say, okay, um, 8 8 to the 16, and what is the remainder? The remainder is what? The remainder is 4. Okay, and what we have is we bring this number here. Okay, and we say, okay, 4 to the 8 and the remainder is 0. Okay, so finally what is the GCD? So GCD is this number. Okay, when you get a remainder 0 and whatever is here, this becomes the GCD. Okay, or you can say you keep 0 here, you put 4 here, and then finally you can say, okay, this 4 is the GCD. Okay, if it sounds confusing, let's take another example. Let's take an example of the numbers 12 and 20. Okay, let's say a is 20 and b is 12. Okay, so what I can do, I keep 20 inside, I keep 12 outside. I say 12 ones are 12. I'm left with 8. I bring this 12 here. I say 8 ones are 8. I'm left with the remainder 4. And inside I put this number 8. I say 4 into 2 is 8. The remainder is 0. And I put this 4 here. Okay, so this 4 is my GCD. So this is like a long division kind of a method. This we generally do on pen and paper. And now we can see that we are reducing the problem every time. So what is this number? This number is a. What is this number? B. So we are effectively saying GCD of the numbers a comma b is nothing but, it is same as we are solving the same problem again here. Okay, so what is this term and what is this term? Let me just tell you. So the first term, that is your b, this is nothing but, this is the remainder. Okay, So this is nothing but this is the remainder that is left when you divide a with b. Okay, so this is 20 mod 12, so I can say this term is nothing but a modulus b. Okay, and what is the term here? What is the term that is taking place of a? Let's say this is a dash and this is b dash. So I'm writing a dash as what is a dash? A dash is this b. So this is what? So I'm saying in one step I can reduce GCD of AB to GCD of B comma A modulus B. Okay, so this is one this is the recursive definition of GCD. Second is we stop at a case. Okay, so we see when the value of this number, when this value of a number becomes 0. So basically I say GCD of, okay, let's say this number is again a dash and this is b dash. So GCD of some number a followed by 0 when the value of b becomes 0 is nothing but the number a. Okay, so this is what is nothing but the number a. Okay, that's what we have. So clearly using these two things we can write our code for finding out the greatest common divisor. So I hope you understood the Euclid's algorithm, and now what we are going to do, we are going to either iteratively or recursively you can build this algorithm and you can find GCD of any two numbers. Okay, so let's see the code in the next video, and that's all. Hi everyone, so in this lecture we are going to code Euclid's algorithm for finding out GCD. So let's see. So what we are going to do, we are going to make a recursive function in GCD which gets two numbers int a and b. And now what we are going to say, we have a base case. If the number b is 0, then GCD is a. Otherwise we can say return GCD of what? We said we will replace a with b and we will replace b with a mod b, and that's it. So maybe I can say int ab scene ab, and I can say out GCD of a and b. So let's build this code, and let's also try to run our code now. So I can say dot slash GCD. I give 8 and 20, so I get the output as 4. Let me give 5 and 35, so I get 5, which is fine. Maybe 40 and 60, so I get 20 as the output. So that means this is working perfectly fine. Now what we can do is we can dry run this code just to see what happens in the recursive call. Okay, so let me give you an example of let's say we are making recursive calls. So we have a call stack. Okay, and in the beginning in the call stack we make the first call. Let's say the number a is 20 and let's say b is 12. So what we do, we pass these numbers. Okay, so we pass 12 and 20. Then what happens is we divide. Okay, we divide. So when you divide 20 with 12, what is the remainder that is left? The remainder is nothing but 8. So I'm writing b here and I'm writing a here. So it becomes 8. And what is a? So basically 12 comes here. Okay, so 12 becomes the new a. So 12 when divided by 8 leaves the remainder 4, and 8 comes here. Then 8 when divided by 4 leaves the remainder 0, and 4 comes here. Okay, so now if you look carefully, this is the value of b dash and a dash, or whatever you want to call it as. So when this value of b is 0, so I say return a. So effectively from this call we are returning a, that is 4. So this call returns 4, this call returns 4, and hence in the main we get an answer as 4. Okay, so this is how we get the answer as 4 for this given input. I hope this is clear to you, and that's all for this video. Hi, so in this lecture we are going to talk about the complexity of Euclid's algorithm for finding out GCD. So let's see how we can find out the complexity of this algorithm. Okay, so let's see. So one thing we have seen is in this algorithm, what we are saying is GCD of a comma b is nothing but we are reducing it to GCD of b and a modulus b. Okay, and we also know, let's say this term a modulus b, we are denoting it using a variable x, and we know the value of x would be less than, it would lie in the range 0. Okay, so when you do a mod of some number with some number b, so then that value would lie in this range 0 to b minus 1. Okay, so if you do some number mod 5, okay, so that value would lie in the range 0 to 4. Okay, you cannot have 5 as the answer. So what I'm saying is, this is one thing. Okay, this is one thing that we have seen. Another thing is we can also write a modulus b. We can write that as x, that is nothing but a modulus b. This can be written as a minus a by b into b. Okay, for example, if a is, let's say, 39, and if, let's say, b is 14, then we can write this 39 modulus 14 as 39 minus the nearest multiple of 14. The nearest multiple of 14 is 28. How do you get it? You get it by taking a floor, 39 upon 14, the value is 2, multiplied with 14. Okay, so this is nothing but 39 minus 28, that is 11. So this equation is also correct. So we are taking a floor here. Okay, we are finding out the nearest multiple and we are subtracting it from a. So now this means that a, now what would be the value of this term? Okay, what would be the value of this term? So if a is greater than b, the minimum value of this term would be 1. Okay, so that means a modulus b would be less than or equal to a minus b. Okay, so if I just put the minimum value as 1, the maximum, the value could be 2 also. That means it would be less than or equal to 1. So I'm talking about this term. So the minimum value of this term is 1. Okay, that means if the value is 2, then a modulus b would be less than a minus b. So from this equation we have that this is equation 2. Okay, so from equation 1 and equation 2, what we can say is, from here we are saying that x is less than b. Okay, we are saying that if you just add these two equations, okay, so this is also x. So if you add this part and if you add this part, so once you're saying that x is less than a minus b, okay, and x is also less than equal to b minus 1. So if you add them up, so it becomes 2x equals a minus b plus b minus 1. So it becomes 2x is less than equal to a minus 1. Or you can say, if I just remove this term, okay, if I just add a 1 here, okay, so, or I can say 2x is less than what? 2x is less than a. Okay, why? Because I removed this term minus 1 and I say, okay, 2x must be less than a. That means x must be less than a by 2. Okay, so this is an important result, and we are going to use this result to prove that this algorithm is a logarithmic, works in a logarithmic complexity. Now what we have learned is that GCD of this number a comma b, okay, so let's write again. So we have written this thing, this result we have already written. So we said GCD of a comma b can be reduced to GCD of b comma a mod b, which is x, and here we can write this number as a by 2. This can be further reduced to, in one more step, as GCD of a by 2 comma, okay, something less than a by 2, I'm saying, okay, or in the worst case that value would be a by 2, and then a by 2 modulus b. Okay, a by 2 modulus b. So effectively what you can say is, in step 1 and in step 2, So you're reducing a problem size to almost half in 2 steps. Okay, so from, if let's say if a is of the order n, then this n will go to n by 2 in 2 steps, then it will go to n by 4, then it will go to n by 8, and so on. Ultimately, to reach 1, it will just take log of n steps. Okay, so I can say GCD of a comma b can be find out in log of a of time to the base 2. The complexity of this algorithm is actually logarithmic, and that's why it is much better than the brute force approach that we have seen. Okay, and logarithmic is very fast. So I hope you understood the complexity, and that's all for this video. Hi everyone, in this lecture we are going to talk about another algorithm that is known as extended Euclid's algorithm. So let's talk about this algorithm and we'll see where it is useful. So basically, sometimes you might be given a equation like this: ax plus by equals GCD of a comma b. Okay, so right now this ab is given to us. Okay, so ab is the part of input. Okay, that means you might be given something of this kind. Let's say 18x plus 30y, that is equal to, let's say, GCD of 18 and 30. Okay, so what you need to do is you need to find the values of x and y. Okay, find the values of x and y that satisfy this particular equation. Okay, so this is what we need to find out. Now you may ask why we are doing this. The reason is this kind of algorithm is useful in two applications which we are going to do little later on. One is finding the multiplicative modulo inverse, and second is finding the solutions to linear Diophantine equations. Okay, which may again have some real life applications as well. So we now need to see how do we find the solution to this equation: ax plus by equals GCD of a comma b. Okay, so I'm just writing it down here: equals GCD of a comma b. So now what we have learned from the Euclid's algorithm is that we can break this down. We can write GCD of AB, GCD of a comma b is same as GCD of what? GCD of b followed by a modulus b. This we have already seen that this is true. Now what we are saying is, in this step we are going to reduce this equation. Okay, so we can say, let me just write it like this. So what we are doing, we are replacing a with b and we are replacing b with a mod b. So let me just replace it here as well. Let's put a as b, so it becomes b followed by some x1. Okay, because the values of x and y will also change if you change the coefficients here. So I'm just saying that these two equations are going to be equivalent. Okay, so b would be like a modulus b, this y would be something else, that would be like y1, and this is equal to GCD of, again replace a with b and b with a modulus b. Okay, so this is what we have done, and we have also seen one result, that a modulus b can be written as a minus the nearest multiple of b. Okay, so that we derived using this floor value. Okay, so this is a floor. So this is another result that we have seen already. So now let me just try to rearrange the terms. So this equation now becomes bx1 plus, I will substitute the value of a modulus b with this value. So I can say it is nothing but a minus a by b into b multiplied with y1. Okay, and this is again equal to GCD of b a mod b, or you can write it as GCD of ab. That is also fine, because both the GCDs are going to give the same result. So now this can be written as so what we are going to do is, we are going to combine the b's together. Okay, we want to combine the b's together and we will keep a separate. So we can say this would become bx1 minus a by b a by b and multiplied with y1. So this y1 will get multiplied and we are taking this b outside. Okay, and plus it would be a y1, that is equal to gcd of a comma b. Now this is a very important equation and this will help us to reach a result. Let me just call this as equation number 2 and let me call the original equation as equation number 1. If I now write the equation number 1 and equation number 2 here, okay, so I'll just write it like here. It is what ax plus this term by, so we have b and y. So I'm rearranging the terms so that we can equate the coefficients here, and that is equal to gcd of a comma b. So this is coming from equation number 1. Okay, so now what is the idea here? What is the idea or the goal? Okay, so we basically want to write down the values of so we can compare b and b, we can compare a and a. That basically means if we can also compare the coefficients. Okay, so I'm going to write an important result here, so let me just tell you. So now what you can do is you can say that in this updated equation, okay, in this reduced equation, let me just call it as a reduced equation. In the reduced equation you can compare, okay, that what is the relationship between this y and this coefficient, what is the relationship between this x and this y1. So effectively we can say that our x is equal to y1, okay, and our y is equal to x1 minus a by b into y1. So now this is an important result and this is the result of extended Euclid's algorithm. This is what it states. And how do we interpret this? Where do we use this? We are going to discuss it very shortly. Okay, so this is the result of extended Euclid's algorithm. So basically what why now it might be little unintuitive why we are doing this, where it will be used. So for that we are going to see an example in the next video. Right now you should note down this result and we are going to use this result in the next lecture. Okay, so that's all for this video, but it's not yet complete. So let's see the application of this result in the next lecture. Okay, it will help us to reach a solution for this particular equation and we would be able to extract the values of x and y from this result. Okay, so okay, let's meet in the next video. Hi everyone, so now let's see how we can use the result that we derived in the previous video to solve a equation of the form ax plus by equals gcd of ab. So let me take an example and show it to you how this result can be used. Let us first write the result. So we said we had an equation of the form ax plus by equals gcd of a comma b. We reduced it. Okay, we said okay, we reduce it to an equation of the form bx1 minus a by b, or let me just write it by rearranging the term. So this becomes a y1 plus b x1 minus a by b, the floor of this value, into y1 equals the same value, that is gcd of ab. Okay, so same. So we derived this result that in the parent equation the value of x is equal to y1 and the value of y is nothing but it can be written as x1 minus a by b y1. Okay, this is what it is. So this we called as a result And now we actually need to see how this result is helpful or how it can solve this particular equation. So let us take a equation. So let me use a different color. So let's have this equation. Let's say a is 18 and b is 30, that is given to us. So this automatically forms the equation ax plus by equals to gcd of ab. So we can say 18x plus 30y, this is equal to gcd of 18 and 30. So we said we will try to reduce this equation. Okay, so I don't know what would be the value of the updated so GCD of 18 and 30. So we said this is nothing but GCD of what? GCD of AB. A comma B is nothing but GCD of B comma A mod B. Okay. So this becomes GCD of 30 and 18 mod 30 is nothing but 18. Okay. So effectively you can say if the first number is smaller, then in the first step these two numbers would be swapped and then the process would start of reducing the numbers. Okay, so then this becomes what? This becomes 30. Now x is going to change. X would be some x1 plus 18 times some y1, and this should be equal to gcd of 30 comma 18. So we can reduce it further. Okay, so first I will write the right hand side. So if I do 18 would come here. Okay, and this number would be 30 mod 18, that would be 12. That means it can be written as 18 times x2 plus 12 times y2. This is equal to this equation. We are going to reduce it further. So it becomes GCD of what? 12 comes here and it becomes 18 mod 12, that is 6. So it becomes 12 times some x3 plus 6 times some y3 equal to GCD of this. Let's keep on doing this until we don't get a value. So it becomes GCD of 6 comma 0. Okay, and now this becomes what? This becomes 6 times x4 plus 0 times y4, that is equal to GCD of 6 comma 0. So now we know the result, that what? So let us first find out the value of x4. So from here we can say the value of x4 is nothing but GCD of 6 and 0. So when this hits a base case, okay, this is like a base case. In the base case we can say when b is 0, then it is nothing but 6. So 6 times x4 is 6. So x4 is 6 upon 6, that is equal to 1. So we know the value of x4 is now 1. Okay, so this also gives us the value of y4. So what would be y4? So I can say so GCD of this would be 6. Okay, so 6 times 1 plus 0 times y4, this is equal to 6. So 0 times y4 is 0. So y4 is also 0. Okay, so y4 is, let's say, 0. We don't need to put any value in y4. So now what we want to do is, so we can say in this equation the values of x4 is 1. Okay, the value of y is 0. What about this equation? Okay, so you can check if you put these values of x and y, then this equation is satisfied. So now you want to find out the values of x3 and y3. So how do you find x3? So basically this formula says this is about the child equation. So if you know the result of the child equation, then you can compute x and y for the given equation. So the x is same as y1. So in this case this x would be same as this y. So x3 would be equal to, effectively now we are going to use this formula, current x is same as y, that is coming from the child, and the current y is nothing but x minus a by b in this particular equation multiplied with y. Okay, so now what is the current x? That is y, so it becomes 0. So effectively we are picking the value from here, and the other value is what? X minus, so x is what? X is 1, so effectively it is 1 minus a by b. So a is 12, b is 6, so 12 by 6 into y. So what is y? So y is 0 here, so it is nothing but 0. It becomes 1 minus 0, that is 1. So if you put 12 times 0 plus 6 times 1, it becomes GCD of 12 and 6, that is equal to 6. That means this equation is also satisfied. So the values of x3 and y3 are nothing but 0 and 1. Now we need to find out the x and y for this equation. So x2 would be nothing but, that would be equal to y3. So x2 would be nothing but 1. Okay. And if you put this value as 1, then what should be the y? So the current y should be equal to what? X minus, so x is 0, minus a by b, so 18 by 12, that is 1, into y. What is y here? That is 1. So it is nothing but minus 1. So you can verify that 18 times 1 minus 12 times plus 12 into minus 1, this gives an answer 6, which is equal to GCD of 18 and 12. So this equation is also satisfied. Now let's come to this equation. So now this x1 would be nothing but equal to this y2, that is equal to minus 1. And how to calculate the value of y? So it is nothing but x minus, so x is what? 1. So 1 minus a by b, that is 30 upon 18. Okay, that is again 1, multiplied with y. So what is y? That is minus 1. Okay, so it becomes 1 minus minus 1, that is 1 plus 1, that is 2. So this value should be nothing but 2. Okay, you can verify. So it becomes minus 30 plus 18 into 2, that is 36. So 36 minus 36, that is equal to GCD of 30 and 18. That's fine. And here you say, okay, this value is nothing but 2 because it is coming from here. And how do you calculate y? So it is nothing but x minus a by b. So x is what? X is minus 1 minus a by b, that is 30 upon 18. Okay, sorry, 18 upon 30. Okay, 18 upon 30, that would be 0, multiplied with y. So what is y? Y is 2. So 0 into something is 0, so it is minus 1. Okay, so now you can see that how we are able to derive the solution for this particular equation. So what we did, we are actually doing a bottom-up approach. So we are going to use something like recursion to hit the base case, and then while coming back we are going to form the values of x and y in each step, and you can verify that this 2 comma minus 1 is the solution to this equation. And you can verify 18 into 2 is 36, minus plus 30 into what? Minus 1. This is equal to GCD of 18 and 30, that is 6. And hence 2 comma minus 1 is the value that satisfies the given equation. Okay, so that's about the theoretical part, what this algorithm is, where it is used, and how it works. In the next video we are going to write the implementation for the same, and that's all for this lecture. Hi everyone, so let's see the code for extended Euclid's algorithm that will help us to solve an equation of this form. Okay, so let's begin. So this is what this is the standard Euclid's algorithm, but now we are going to code the extended Euclid's algorithm. Okay, so maybe I will open up a new file. Let me call as extended gcd.cpp. So first of all, what we are going to do, we are going to write main. In the main we are going to take input the values of a and b, and we need to find out the values x and y such that ax plus by equals GCD of a comma b. Okay, so we need to find out these values x and y. So what we are going to do, we are going to write, okay, int extended Euclid's algorithm. Okay, maybe just call it as extended GCD, and here we are passing the values ab, which are input, and the values x and y that we need to compute. Okay, or another option could be we can actually return a pair of int, that is also fine, or maybe we can also return a vector of two integers, that is also fine. Okay, so we are going to return the values x and y, so no need to pass these values. We are simply going to return a vector of x comma y, that will also work. So in the base case, what we have seen is that if the a becomes 0, okay, if the value of a becomes 0, we can simply say the answer is what? Sorry, this should be b becomes 0. Okay, so when we reduce this, so here we have seen when b becomes 0, we return the GCD as a. So here instead of returning the GCD, we want to return the values of x and y. So what we have seen in the previous example was when you keep on reducing the equations, ultimately we saw for the last equation, like we started from 18x plus 30y equals GCD of 18 and 30. We reduced it further, further, and finally we saw it becomes GCD of some 6, that is a comma 0. Okay, in this case we also saw the equation was like 6x4 plus 054 equals GCD of this. So we saw in the base case this 6 and this 6 would be always same. Okay, this would be like ax plus 0y equals GCD of a comma 0. Okay, so that would be nothing but when b is 0, we say GCD is nothing but a, so it is nothing but ax equal to a. X is always 1 in this case and the value of y is always 0. So in the base case we can say let's return a vector of 1 comma 0, that will do the work for us. In the recursive case, okay, in the recursive case what we are going to do, we are first going to make a call. Okay, we are going to say okay, vector int maybe result from the call, that would be nothing but this is going to be equal to extended GCD, and in a and b what you are going to pass, you are going to pass b and a modulus b. Okay, this is what we have already discussed. So you make a call and this call returns some result. So this vector result contains the small x and the small y. So I can say okay, my x is what or maybe the x from the child. Okay, so x maybe x dash or something, let's say the small x. Okay, the small x is result of 0. Okay, and the small y would be what? Result of 1. And now using this small x and small y, I need to form the values of x and y. So in my case I said my x is nothing but that is equal to small y, and my y is nothing but that is equal to small x minus a by b, that is the floor division, multiplied with y, so that is nothing but small y. So from this I can return a vector of x and y. So that's what we are doing. Okay, so we are reducing our problem, we are breaking it down, okay, until we hit the base case. From the base case we return the result 1 comma 0, and using the result from the sub problem we are forming the result for the current call. Okay, so this is actually a bottom up approach. This is like a bottom up solution building, because we are doing this work after the function call has been made. Okay, so bottom up way of building the solution. Okay, so or maybe you can say while you're coming back from the recursion you are doing the work. Okay, so after recursive call is over. Okay, so this work should be done after the recursive call is over. So let me try to build the code. Okay, the code is building fine, and now we can say int xy. So I can say my result vector int result is nothing but extended GCD, and I give the values of a and b. and here I can say C out result of 0, that is x, and result of y, that is what, a result of 1, that is the value of y. That's it, and we can build the code and we can run it as well. So let us verify our code. So let me run it, /extended gcd. Let me give 18 as 12 as input. So basically you can see 18x plus 12y should be equal to gcd of these two numbers, that should be 6. Okay, and this answer is 6. So 18 into 1 minus 12 into 1, this is also equal to 6. So that means our solution 1 and minus 1 is correct. Let me try with another example. If I give 18 and let's say 30, so it is 2 and minus 1, that means 18 into 2 plus 30 into minus 1, this is also 6. GCD is 6 in this case, 36 minus 30, which is 6, and it is equal to GCD of 18 and 30. So that means the algorithm is working perfectly fine, and this is how we can build the extended Euclid's algorithm. And that's all for this video. Hi everyone, in this lecture we are going to see a small modification so that we can also compute GCD in the extended Euclid's algorithm. Okay, so if you want to compute GCD of two numbers a and b, so what we have discussed is you can simply make a GCD function that takes a and b, and in the base case you write if b is 0, you return the value a. Okay, and otherwise what you do, you call this function GCD recursively and you pass the parameters as same as this one, b and a mod b. Okay, so b and a mod b, this is what we have already discussed, which is the Euclid's algorithm to compute GCD. And we have also seen what is extended Euclid's algorithm to solve an equation of the form ax plus by equals GCD of a comma b. So we have already seen how do we compute two integral values of x and y for this equation using extended Euclid's algorithm. Now what I'm going to do is I'm going to slightly modify this algorithm so that we also get the GCD from this algorithm. Okay, so what I will be doing is I'm returning a vector. So this vector, instead of containing xy, it is now going to contain three values. It is also going to store GCD. So that means from the base case I need to return the GCD. So when b is 0, so we have discussed the GCD is a, so I will also return the value a from this point. And otherwise in the recursive case we return whatever is returned by the recursive function. Okay, so whatever is returned by this recursive call, this is stored in result. So we can say int GCD is nothing but result of 2, because it is a vector that contains 3 entries, and from this call we are going to return the same GCD. So now what is going to happen, this vector is going to contain 3 numbers, so the values of x and y and also the values of GCD. So we can say the GCD is this. Okay, so GCD is nothing but result of 2. So if you want to verify that it is the same GCD, we can even call this function the first one, cout GCD, and we can give the values of a and b as well. So we are now computing GCD using both the functions, that is the Euclid's algorithm, and the first one is extended Euclid's algorithm. So let us run our code, and I need to run extended GCD. So if I give the numbers 10 and 12, so you can see the first one is giving GCD2 and the Euclid's algorithm is also giving GCD2. So that means it's working fine. Let's give 8 and 24. So in both the cases the GCD is 8. Okay, so this is one thing that we have done, and now you may ask where we are going to use it. So you will see very soon in the next lecture when we do multiplicative modulo inverse, we would be using this method to compute the values of x, y and the values of GCD. Okay, so these are the three things that we would be computing given a and b very soon. So although you could have done it using two methods, but this is now not needed once you have written the extended GCD algorithm, because it also gives you the value of GCD. Hi everyone, in this lecture we are going to talk about multiplicative modulo inverse. So what is this multiplicative modulo inverse? So it is defined for two integers a and m. So in the input you are given two integers, one is a, another is m. We want to find the multiplicative modulo inverse of a under modulo m. This is an important statement. A under m. We need to understand what it means. So the multiplicative modulo inverse is an integer x such that a multiplied with x is congruent to 1 modulo m. So this symbol is known as congruent to. So what is the meaning of this particular statement? It basically says when a is multiplied with x, okay, and it has taken a mod with m, which is input, this leaves a remainder 1. Okay, let me give you an example. Let's say you're given in the input the value of a is, let's say, 6, the value of m is, let's say, 7. Okay, so let's put 6 into something that is x. When taken a mod with 7, this leaves a remainder 1. So one thing we should know is the value of multiplicative modulo inverse should lie in the range, it should lie in the range 1 to m minus 1. Okay, so right now we do not know any algorithm to find out this value. So what we can do, we can try a brute force solution. So we can put the value of x as 1. So 6 into 1 mod 7 is not 1. So we try with the next value. 6 into 2 is 12 mod 7 is not 1. We try the next value. 6 into 3 is 18 mod 7 is not 1. Let's make it 4. 24 mod 7 is not 1. Make it 5. 30 mod 7 is not 1. Make it 6. So 6 into 6 mod 7 is 36. Okay, and 36 mod 7 is actually 1. So we can say yes, the value of x should be 6. So we can say 6 is the multiplicative modulo inverse of 6 under modulo 7. Okay, so that is another condition. And there are two things that you should remember. So first thing is the value of multiplicative modulo inverse should lie in this range, and this multiplicative modulo inverse MMI, which I'm calling in short, exists if and only if a and m are relatively prime. If a and m are relatively prime, which effectively means the GCD of a and m should be equal to 1. Okay, this GCD should be equal to 1. So these are the two conditions. So this is basically a condition, and this is, you can say, it's a fact. The value of multiplicative modulo inverse should be in the range 1 to m minus 1. Okay, let me give you another example. This is example 1. Let's see another example. So let's say the value of a is 8, the value of m is, let's say, again 7. You can see the GCD of a and m is 1. That means the multiplicative modulo inverse should exist. So 8 into something taken a mod with 7 should be equal to 1. So if you carefully see, if you start with a brute force approach and if you put this value as 1, then 8 mod 7 is 1. So we can say 1 is multiplicative modulo inverse of 8 under modulo 7. Okay, so I hope you got a little bit idea about what is a multiplicative modulo inverse, and in the next lecture we will see an algorithm to find multiplicative modulo inverse. Hi everyone, in this lecture we are going to see an algorithm to compute the multiplicative modulo inverse of a under modulo m. Okay, so we have already discussed the brute force approach that will take order of m time to compute the multiplicative modulo inverse. But in this lecture, what we are going to do, we are going to look at extended Euclid's algorithm to compute the multiplicative modulo inverse. Okay, so what we have learned in extended Euclid's algorithm is that given two integers a and b, this algorithm helps us to find an equation of the form ax plus by, which is equal to GCD of a and b. And this MMI tells us that for MMI to exist, GCD of a and m must be 1. Okay, so this multiplicative modulo inverse we have discussed, if it exists if and only if GCD of a and m is 1, that means a and m are co-prime. So this is what extended Euclid algorithm is telling us. Now what we are going to do, we are going to substitute the value of a with a, and we are going to put b equal to m in the above formula. If I just replace the value of b with the value m in the above formula, and so what we can do, we can say ax plus my, this is equal to GCD of a and m. And we also know that GCD of a and m is equal to 1. So this is equal to 1. So ax plus my, this is equal to 1. So if you take modulo on both sides, okay, if you take modulo on both sides, it would become ax mod m plus my mod m. Okay, so my mod m is nothing but 0. This is equal to 1 mod m. Okay, so effectively this equation becomes same as this one. So that means ax mod m is equal to 1, or ax is congruent to 1 mod m. Okay, so that is effectively this equation. So what we are trying to say is, if you find the solution to this particular equation, then you will get the desired value. So what would be the value of so this equation can easily be solved using extended Euclid's algorithm that we have already seen, and that algorithm gives us the three values. It gives us the values x, it gives us the value y, and it also gives us GCD. GCD is 1, we always know. The value of y, although the algorithm will give us, but it is not needed. The value of x is what would constitute your multiplicative modulo inverse. So that's where extended Euclid algorithm we are going to use to compute the multiplicative modulo inverse. Okay, so this is the value of multiplicative modulo inverse that we want to compute. So let's see in the coding video how do we actually build this algorithm and compute the multiplicative modulo inverse. Hi everyone, so let us see the code for computing multiplicative modulo inverse. So in the input we are going to accept two integers a and m. Okay, so I can say int a and m. I'm going to take those as inputs, and both of them should be co-prime. They should be relatively prime. Okay, and that we will check in the MMI code. So what we are going to do, we are going to say, okay, let's write a function that is mod inverse, okay, or multiplicative mod inverse, whatever you want to call it as. It is accepting two integers a and m, and let us have two values. One is, let me just vector int result, that is equal to extended GCD of this. So we call this method that is going to return us the values of x, y, and GCD. So this is, we give the values of a and m, and now what we can get, the value of x, that is equal to result of 0, and the value of y is not needed, and the value of GCD is needed, so we can say result of 2. So what we can do is, we can say if GCD, if this is not equal to 1, okay, if this is not equal to 1, that means in this case the multiplicative modulo inverse will not exist. So we can print a statement, multiplicative modulo inverse does not exist, and maybe you can return -1. Otherwise, you know, your answer is what? Your answer is nothing but the value of x. Now this x can be negative also. X can be negative also if it is returned by the extended Euclid's algorithm. So just to make it positive and make it in the range of 1 to m minus 1, what we can do is we can take a mod with m and we can add a m here and take a whole mod m. Okay, so this will make sure that our answer lies in the correct range, and from here we can return our answer. Okay, so now let us try to run our code. If I say I want to run I want to find out the multiplicative modulo inverse, that is mod inverse of a and m, and let's see what this gives. So let's say one of the input is 6 and we want to calculate with respect to 7. So we are getting an answer as 6, which is fine. And if I give, let's say 8 and 7, the answer is 1, which is fine. So if you do not do this, if you simply say your answer is equal to x and you build the code, and if you give 6 and 7 as input, so you can see you're getting an answer as -1. Why? So -1 is not in the range 1 to 6, okay, because the value of m is 7. So what we said, we will take a mod with 7, we will add 7 to it, so this becomes 6, and 6 mod 7 is what? It is actually 6. So we can, this is how we convert negative numbers into positives. Okay, and so this is why this step is needed. So I hope you understood the code for multiplicative modulo inverse, and that's all what we need to do. If you have numbers like, let's say 10 and 12, so they don't have a GCD 1, so it says multiplicative modulo inverse does not exist. So that's all for this lecture, and thank you. Hi, so in this lecture we'll talk about linear Diophantine equation. So what is this linear Diophantine equation that we are going to discuss? So an example of linear Diophantine equation is this equation, and where we are given, okay, some a times x plus some b times y, this is equal to c, and we want to find an integral solution that for the values of x and y. So we need to find two integers that if we put the value of x and y, that will satisfy this particular equation. Okay, so it's a single equation, but we have two variables. So a single equation, but we have two variables, so we need to find out one solution, but later on we will prove if one solution exists for this equation. In that case there can be infinitely many solutions possible for this equation. Okay, so if there is a one solution, that then there would be infinitely many solutions. So we will also look at a generalized solution later on for this particular equation. So the question is, we need to find out a solution for this equation. So let us see here. So firstly, what is a Diophantine equation? So a Diophantine equation is a polynomial equation in two or more unknowns such that only integral solutions are required. And what is the problem statement we are solving? So in our problem we are going to we are given three integers, and these three integers are a, b and c, and what we want is we want to determine if the solution has a equation such that x and y are both integral solutions. That this is what we need to solve for. So let us start by saying, let us assume, so the equation is ax plus by, this is equal to sorry, let me say ax plus by, this is equal to c. Okay, and let us say that GCD of a comma b is denoting using the variable g. That means a would be some multiple of g. Okay, so I can write a as some g times into some constant k1, and b can be written as g times some constant k2. Okay, so this is pretty obvious. For example, if 8 and 12 are the values of A and B, then we can say GCD is 4, and A can be written as 4 into 2 and B can be written as 4 into 3. Okay, so that is what we are saying here. So if I replace the values in the equation, so I can write this equation as what? I can write this equation as, if I put A as G times K1, so it becomes G times K1x plus G times K2 into Y. This should be equal to C, or I can say K1x plus K2y. This is equal to C upon G. So effectively what it means is, if K1 if all of these values on the left hand side, everything is an integer on left hand side, then it means the RHS must be an integer. That means this solution is going to have an equation, have a solution if, okay, the solution would exist if and only if C is divisible by G. That means C mod G should be equal to 0, because everything on the left hand side is an integer. The right hand side would be an integer if C is divisible by G. Okay, so and this thing must be an integer, only then the solution will exist. So that is the condition for the solution to exist. If C is divisible by GCD of A and B, in that case this equation will have a solution. Okay, so this equation will have a solution if it satisfies the above condition. Okay, that means the C should be divisible by GCD of A and B. Now let us talk about how do we find out that solution. Okay, the second step is, how do we find out the solution? How to find out the solution? So we can write this equation as AX plus BY equals some constant into G, because we know that C is divisible by G, so C must be a multiple of G. Okay, that's what we can say. And what we can do now is, let us say what we have learned in extended Euclid algorithm, what we have learned is that in that we have already seen how to solve the equation of this particular form, where let us say x naught and y naught is a value that solves this equation. Okay, that solves the given equation. Okay, so let's write this value as ax naught plus by naught. This is equal to C, and C we have put as K times G. So what we are going to do now is, we are basically saying that we have also seen an equation of the form ax plus by equals GCD of A comma B. Okay, so this kind of equation we have already seen, and we know the solution for this equation is given by the extended Euclid's method. Okay, extended Euclid's method. And let us assume that x1 and y, x dash and y dash are the solution for this equation. Okay, so what we can say ax dash plus by dash equals GCD of A comma B. So x dash and y dash we can already compute using the extended Euclid's method. So can you relate what is the difference in this equation and this equation? So effectively this GCD is same. This GCD is nothing but this GCD of A comma B. So effectively in this equation what you have done, you have multiplied everything with K. So this is nothing but this is multiplied with K times. So if you want to produce the same result here, so what do you need to do? You need to multiply this with K and y dash with K and x dash with K. So effectively if you now compare the equation number 1 with equation number 2, that effectively it becomes that the value of x in this case would be nothing but x k multiplied with x dash. So where x dash is the solution coming from the above equation, okay? Or let's say the value of x naught. X naught is a solution, okay? X naught is nothing but k times x dash, and the value of y naught is nothing but k times y dash, where x dash and y dash are solutions of this particular equation, okay? Where x dash and y dash are the solutions from this particular equation. So, and once we know the solutions, we can easily find out the solutions for this equation as well. So they are nothing but they are k times the solutions of this particular equation, okay? And these solutions, we know they are coming from extended Euclid's method that we have already seen. So what you need to do, you just need to multiply whatever solution you get from extended Euclid's method with the value k. And what is the value of k? K is nothing but, we have written C as k times GCD of AB, okay? The value of k is nothing but C divided by GCD of AB. So we know the value k, we know the solution x dash, we know the value y dash, and hence we know what is the value of x naught and what is the value of y naught that is going to satisfy the original equation, okay? So this is how we can derive the solution for this equation using extended Euclid's method. Hi everyone, in this lecture we are going to look at the generalized solution for the given equation, okay? So basically what we have done is we have figured out one solution using extended Euclid's method, and we said the values of x is going to be x naught and the value of y is going to be y naught, such that they satisfy the above equation. So putting ax naught plus by naught satisfies the given equation. And now what I want to prove is, I want to show you that if there is one solution, then there are infinitely many solutions possible for the above equation, okay? So the family of solutions is denoted by, let's say, x comma y. The possible set of values that these x and y can take, they are nothing but x naught plus b by g into t, where t is a parameter, and y naught minus a by g into t. So if you so what b is already given in the problem statement, okay? G you can compute. G is nothing but GCD of a and b, okay? A is already given in the question. And what is t? T is a parameter, so you can put t as 1, you can put t as a 2, okay? So t can take a lot of values, okay? So t can take infinitely many values, and you will get infinite number of solutions that will satisfy the above equation. So we already know that this equation is true. So what we want to prove is that this solution is also possible for the given equation. So what we are going to do, we are going to replace the value of x with x naught plus b by g into t, and we are going to replace the value of y with y naught minus a by g into t. And let's see what this becomes. It becomes ax naught plus ab upon gt plus by naught minus ab upon g into t. So now you can clearly see that these two variables get cancelled off, and what you get ax naught plus by naught, and this is equal to c. This we have already seen. So this is equal to c, and hence what we can say is these two this family of solutions will also satisfy the given equation. And hence if you are able to find out one solution, you can claim that there exists a family of solutions, and by putting various values of t, you can get infinitely many solutions for a linear Diophantine equation. So that's all for this video, and thanks a lot.